Up to this point, we've been using ANOVA primarily to answer one question. Are there any treatment differences present in the experiment? The ANOVA F-test is useful because it tells us whether there is evidence that at least one treatment mean differs from the others. However, in practice, that's usually not the question researchers really care about. If I'm running an experiment, I don't just want to know that something changed. I want to know which treatments differ, how they differ, and whether those differences are meaningful. That's the focus of today's lecture. We're going to discuss methods for making inferences about treatment means and specific comparisons among treatment means. We'll learn how to construct confidence intervals and hypothesis tests for these comparisons, and later we'll discuss what happens when we want to make many comparisons at the same time. One of the most useful tools in analysis of variance is the contrast. A contrast is simply a linear combination of treatment means where the coefficients sum to zero. The key idea is that a contrast allows us to ask a very specific scientific question. Instead of comparing all treatments simultaneously, we can compare exactly the groups that interest us. For example, we might compare a control group against the average of several treatment groups. We might compare low doses versus high doses, or we might compare one treatment against another. Notice that the coefficients must sum to zero. Why is that important? The reason is that this condition ensures we're measuring a difference among treatment means rather than an overall level. When the coefficients sum to zero, the contrast represents a comparison. That's exactly what we want. Let's review the statistical background. For a completely randomized one-factor ANOVA, every estimable contrast can be estimated using the sample means. The estimate is obtained by replacing the treatment means with their corresponding sample means. The variance of that estimate depends on three things: the coefficients in the contrast, the sample sizes, and the mean square error from ANOVA. One important observation is that once we've fit the ANOVA model, we can investigate many different contrasts without fitting additional models. Everything we need is already contained in the treatment means and the MSE. Let's consider the simplest possible contrast. Here we're comparing treatment 1 and treatment 2. The coefficient for treatment 1 is +1, and the coefficient for treatment 2 is -1. When we write the contrast this way, we're simply calculating treatment 1 minus treatment 2. Now ask yourself, what does it mean if this contrast equals 0? If the contrast equals 0, then the two treatment means are identical. This is the basic idea behind many comparison procedures. Most pairwise comparisons are really just simple contrasts like this. Once we've estimated a contrast, we can construct a confidence interval for it. The structure should look familiar. It's estimate plus or minus a critical value multiplied by a standard error. The quantity attached to the critical value is often called the minimum significant difference, or MSD. Conceptually, the MSD tells us how large a contrast must be before we consider it statistically meaningful. If the confidence interval contains 0, then 0 is a plausible value for the contrast and we fail to reject the null hypothesis. If the interval does not contain 0, then we have evidence that the contrast differs significantly from 0. Let's work through an example. Researchers wanted to evaluate 7 different membrane filters used for growing bacterial colonies. Some of these filters arrived pre-sterilized, while others did not. The response variable was the number of bacterial colonies observed. Before we start calculating anything, think about the scientific question. We're not interested in comparing every individual filter to every other filter. Instead, we're asking whether the pre-sterilized filters differ from the non-pre-sterilized filters on average. That's exactly the type of question contrasts we're designed to answer. To answer this question, we first need to define the hypotheses. The null hypothesis states that the average effect of the pre-sterilized filters equals the average effect of the non-pre-sterilized filters. The alternative hypothesis states that these averages are different. Notice that we're comparing groups of treatments rather than individual treatments. This is one of the strengths of contrasts. They allow us to combine treatment means in a way that directly addresses the scientific question. Now let's perform the calculations. The most important step here is setting up the coefficients correctly. The coefficients should reflect the comparison we want to make. Once the coefficients are established, the arithmetic is fairly straightforward. When students make mistakes with contrasts, it's usually because the contrast itself was defined incorrectly, not because of the calculations. So always spend extra time thinking about what comparison you want before you start computing. Next, we conduct the hypothesis test. Using the estimated contrast, its standard error, and the appropriate t-distribution, we obtain a test statistic and a p-value. Remember what the p-value represents. It tells us how unusual our observed contrast would be if the null hypothesis were actually true. A small p-value provides evidence against the null hypothesis. A large p-value indicates that the observed difference could easily be explained by random variation. Now let's construct the confidence interval. Notice that this interval provides more information than the hypothesis test alone. The hypothesis test tells us whether a difference exists. The confidence interval tells us the range of plausible values for that difference. This is one reason many statisticians prefer confidence intervals. They provide both significance information and effect size information simultaneously. Our p-value is greater than 0.05, so we fail to reject the null hypothesis. Likewise, the confidence interval contains 0. Both approaches lead to the same conclusion. Based on the data from this experiment, there is insufficient evidence to conclude that pre-sterilized and non-pre-sterilized filters differ in their effects on colony counts. It's important to phrase this carefully. We are not proving that the filters are identical. We're simply saying that this experiment did not provide strong enough evidence to detect a difference. Now we're switching gears a little bit. So far, we've treated treatment levels as categories. We compare treatment means and ask whether differences exist among them. But suppose our factor is quantitative. Maybe it's temperature, pressure, concentration, dosage, or time. In this example, we're looking at temperature. If our factor is quantitative, then simply testing whether treatment means differ may not be taking advantage of all the information available. Think about it. The difference between 50 and 100 degrees has meaning. The difference between 100 and 150 degrees has meaning as well. The treatment levels have a natural ordering. So instead of only asking whether treatment means differ, we can ask whether there is a pattern in the response as the factor changes. That's where orthogonal polynomials become useful. When a quantitative factor has multiple levels, we can investigate the shape of the relationship between the factor and the response. For 4 levels, we can test for a linear trend, a quadratic trend, or a cubic trend. The idea is to partition the treatment variation into separate components corresponding to different curve shapes. Orthogonal polynomials provide a set of coefficients that isolate each of these patterns. A linear trend tells us the response generally increases or decreases as the factor increases. A quadratic trend indicates curvature. Higher-order terms represent increasingly complex relationships. The coefficients used for these contrasts are available in tables, such as Table A.2 in your textbook. Let's look at an example. Researchers wanted to study the effect of pump speed on fluid flow rate in a heart-lung pump. The treatment factor is revolutions per minute, or RPM. The levels are 50, 75, 100, 125, and 150 revolutions per minute. There are really 2 questions we want to answer. First, is there evidence that the treatment means differ? Second, if there is a difference, can we describe the relationship between RPM and flow rate using a mathematical pattern such as a linear or quadratic trend? Orthogonal polynomial contrasts allow us to answer both questions. These are the orthogonal polynomial coefficients used for this experiment. Each row corresponds to a different trend component. The linear coefficients test whether the response changes in a straight-line fashion. The quadratic coefficients test for curvature. The cubic and quartic coefficients test more complicated patterns. One important feature is that these contrasts are orthogonal. That means the information captured by one contrast does not overlap with the information captured by another. As a result, we can interpret each component independently. If you're using SAS, this is how you would implement the analysis. Notice that each contrast statement corresponds to one polynomial component. The first statement tests for a linear trend. The second tests for a quadratic trend. The third tests for a cubic trend. The fourth tests for a quartic trend. The nice thing about software is that once we've identified the coefficients, SAS handles all of the calculations automatically. Our primary responsibility is understanding what each test represents. Whenever you're looking at output like this, start with the overall ANOVA table. The ANOVA tells us whether there is evidence of a treatment effect. The p-value is extremely small, so we conclude that RPM affects flow rate. Next, we move to the orthogonal polynomial contrasts. Notice that the linear contrast explains almost all of the treatment variation. The p-value for the linear component is essentially 0. However, the quadratic, cubic, and quartic components are all non-significant. That tells us the relationship is overwhelmingly linear. So what do we conclude from this analysis? First, there is strong evidence that RPM affects flow rate. Second, the relationship appears to be linear. In practical terms, that means increasing RPM results in a predictable increase in flow rate. We do not need a more complicated model because the higher-order polynomial terms are not significant. Whenever possible, we prefer the simplest model that adequately describes the data, and in this case, a linear relationship appears sufficient. Now we're moving into one of the most important topics in applied statistics: multiple comparisons. Suppose we calculate several confidence intervals or perform several hypothesis tests. Most students initially assume that if each test is performed at a 5% significance level, everything is fine. Unfortunately, that's not true. Every additional test creates another opportunity to make a mistake. As the number of tests increases, the probability of making at least one incorrect conclusion increases as well. This is known as the multiple comparisons problem. Let's look at the probability framework behind the problem. Suppose we create m confidence intervals. Each interval has a confidence level of 1 minus alpha. Define an event where an interval correctly contains the true parameter. Then define the complementary event where it does not. The probability that all intervals are correct depends on the joint behavior of all these events. As the number of intervals grows, the probability that every interval is simultaneously correct decreases. This slide makes the idea more concrete. The probability that all intervals are correct is equal to 1 minus the probability that at least one interval is incorrect. With only 2 intervals, the issue may not seem severe. However, as the number of intervals increases, the probability of at least one error can become surprisingly large. That's why we need procedures specifically designed to control error rates across entire families of comparisons. This leads us to the concept of experimentwise error rate. The experimentwise error rate is the probability of making at least one incorrect conclusion among the entire collection of comparisons. Notice that this quantity increases as the number of comparisons increases. Researchers often care much more about the experimentwise error rate than the error rate of an individual comparison because they want confidence in the overall set of conclusions. The goal of multiple comparison procedures is to keep this overall error rate under control. These examples illustrate how quickly the problem can develop. If we construct 6 intervals at the 5% level, the probability that all 6 are simultaneously correct can drop substantially. With 10 intervals, the situation becomes even worse. By the time we reach 20 or more comparisons, the cumulative error can become so large that the results are difficult to trust. Exactly the same issue occurs with hypothesis tests. The more tests we perform, the greater the chance of obtaining a false positive somewhere in the analysis. Over the years, statisticians have developed a variety of methods to address this problem. Different methods are appropriate for different scientific goals. Some methods are best when only a few specific contrasts are of interest. Others are designed for all pairwise comparisons. Still others are intended for comparisons against a control treatment. The method we choose depends on the structure of the experiment and the questions we want to answer. One of the most important distinctions in multiple comparisons is whether the contrasts were planned before the data were collected. Pre-planned contrasts are identified in advance based on scientific objectives. This is generally considered the best practice because it reduces the risk of data-driven conclusions. When designing an experiment, we should think carefully about which comparisons are truly important and ensure that the experiment is capable of estimating those contrasts efficiently. The contrast from our filter example is a good example of a preplanned contrast because it was motivated by a specific scientific question before the data were analyzed. Now let's talk about something statisticians worry about quite a bit: data snooping. Data snooping occurs when we allow the data themselves to suggest which comparisons we should investigate. Imagine collecting data, looking through the results, and then noticing an interesting pattern. Maybe one treatment seems unusually high or unusually low. At that point, it's tempting to create a new contrast specifically designed to highlight that pattern. The problem is that this process increases the probability of finding significance simply by chance. In other words, the more we search through the data looking for interesting results, the greater the likelihood that we'll discover something that isn't really there. This doesn't mean exploration is bad. Exploration is often valuable. However, we need statistical methods that account for the fact that these comparisons were chosen after seeing the data. We're now going to look at several methods for constructing simultaneous confidence intervals. Although the formulas differ, all of these procedures have the same basic objective. They attempt to control the overall confidence level across an entire collection of intervals. In other words, rather than guaranteeing confidence for each interval individually, they guarantee confidence for the entire family of intervals. The trade-off is that maintaining this higher level of protection generally requires wider confidence intervals. The next several slides compare some of the most common approaches. The first method we'll discuss is the Bonferroni procedure. The Bonferroni method is one of the simplest and most widely used approaches for multiple comparisons. It works for any set of preplanned estimable contrasts. One major advantage is that it can be applied to virtually any experimental design. Another advantage is that when the number of planned comparisons is relatively small, the resulting intervals are often reasonably short. The major limitation is that the comparisons must be identified before the data are examined. Because of this requirement, Bonferroni is generally not appropriate for data snooping situations. The Scheffe method takes a very different approach. Instead of protecting only a specific set of planned contrasts, Scheffe protects all possible contrasts simultaneously. This makes it extremely flexible. If, after seeing the data, you decide to investigate additional contrasts, Scheffe still provides valid inference. The price we pay for this flexibility is wider confidence intervals. In general, Scheffe intervals tend to be more conservative than Bonferroni intervals when only a small number of contrasts are of interest. However, when many contrasts are being considered, Scheffe often becomes more attractive. Tukey's method is designed specifically for pairwise comparisons. If your primary goal is comparing every treatment mean with every other treatment mean, Tukey's procedure is usually one of the best choices. Because it focuses specifically on pairwise differences, it often produces shorter intervals than more general methods. For balanced designs, Tukey's method provides exact control of the experimentwise error rate. For unbalanced designs, the method is slightly conservative but still performs very well. Whenever all pairwise comparisons are of interest, Tukey should be one of the first methods you consider. Dinette's method is specialized for a very common experimental situation. Many experiments include a control treatment and several alternative treatments. In these studies, we're often interested only in comparing each treatment to the control. We usually don't care about comparing treatment A to treatment B or treatment B to treatment C. Dinette's method takes advantage of this structure and provides more efficient intervals than a general multiple comparison procedure would. This is especially common in pharmaceutical studies, toxicology studies, and industrial experiments. Su's method addresses a slightly different question. Instead of comparing everything to a control, we're interested in identifying the best treatment. Once the best treatment has been identified, we then determine which treatments are significantly worse than that best treatment. This approach is useful when the goal is selection. For example, if we're screening manufacturing processes, fertilizer formulations, or product designs, we may simply want to know which options remain competitive with the best performer. Let's look more closely at how the Bonferroni procedure works. The underlying idea is remarkably simple. Suppose we want the overall error rate across all comparisons to be alpha. Rather than giving each comparison the full alpha level, we divide the allowable error among the comparisons. As the number of comparisons increases, the significance level assigned to each individual comparison becomes smaller. This forces the critical values to become larger, which in turn widens the confidence intervals. The result is better protection against false positives. Let's return to our filter experiment. Now suppose that before collecting any data, we identified 3 specific contrasts that we wanted to investigate. Because these contrasts were planned in advance, the Bonferroni method is appropriate. Notice that each contrast corresponds to a particular scientific question. The first compares pre-sterilized versus non-pre-sterilized filters. The key idea is that these comparisons were motivated by subject matter knowledge rather than by patterns observed after examining the data. The remaining planned contrasts address other scientific questions. One compares filters with graduated pore sizes to filters with uniform pore sizes. Another compares filters intended for bacteriological analysis with those intended for sterility testing. Notice how each contrast reflects a meaningful scientific hypothesis. This is exactly what we want when planning an experiment. Rather than testing every possible comparison, we focus on comparisons that have practical importance. Now we begin the actual Bonferroni calculations. The first step is identifying the adjusted critical value. This critical value is larger than the one we would use for an ordinary confidence interval because we're protecting against multiple comparisons. Everything else about the calculation remains familiar. We're still constructing confidence intervals using an estimate plus or minus a margin of error. The only difference is the adjusted critical value. Let's work through the first interval carefully. Notice that we calculate the standard error of the contrast, multiply it by the adjusted critical value, and obtain the minimum significant difference. Once we have that quantity, constructing the confidence interval is straightforward. I encourage you to focus on the structure of the calculation rather than memorizing formulas. Every simultaneous confidence interval procedure follows the same general pattern. After calculating the remaining intervals, we interpret them exactly as we would ordinary confidence intervals. The key question is whether 0 is contained in the interval. Notice that every interval includes 0. Because 0 remains a plausible value for every contrast, we do not have sufficient evidence to conclude that any of these contrasts differ significantly from 0. This illustrates how multiple comparison adjustments often lead to more conservative conclusions. Now let's revisit Scheffe's procedure. One drawback of Bonferroni is that it becomes increasingly conservative as the number of planned comparisons grows. Scheffe addresses this problem by focusing on all possible contrasts simultaneously. The remarkable feature of Scheffe's method is that the interval width depends only on the number of treatments and observations, not on how many contrasts you ultimately decide to examine. This flexibility makes Scheffe particularly attractive when exploratory analysis is important. The theory behind Scheffe's method is elegant. Every possible contrast can be represented as a combination of a smaller set of fundamental contrasts. Scheffe constructs a confidence region that simultaneously protects all of these fundamental contrasts. As a result, every possible contrast automatically receives protection as well. This means we can investigate planned contrasts, unplanned contrasts, and even large collections of contrasts without inflating the overall error rate. That's why Scheffe is often considered one of the most flexible multiple comparison procedures available. Now let's look at the actual Scheffe confidence interval formula. At first glance, the formula may seem intimidating, but conceptually it's doing exactly what we've done before. We're still taking an estimate and adding and subtracting a margin of error. The difference is how the critical value is determined. Instead of using a t-distribution like we did for ordinary confidence intervals, Scheffe uses a critical value derived from the f-distribution. That larger critical value provides protection for all possible contrasts simultaneously. As a result, the intervals are generally wider than ordinary intervals, but they maintain the desired overall confidence level no matter how many contrasts we investigate. Let's revisit the filter experiment one more time. Previously, we examined 3 planned contrasts. Now we're going to expand our investigation and consider additional contrasts as well. This is exactly the type of situation where Scheffe's method shines. Because Scheffe protects all possible contrasts, we don't have to worry about whether a contrast was planned before data collection or identified afterward. The procedure remains valid regardless of how many contrasts we decide to examine. Here we're computing the Scheffe intervals. Notice that we're using the experimental values for alpha, the number of treatments, the total sample size, and the mean square error. Once we obtain the Scheffe critical value, we calculate the minimum significant difference in the same way we've done before. The process is very similar to Bonferroni. The primary difference is the larger critical value resulting from Scheffe's broader protection. These are the remaining confidence intervals. When interpreting a table like this, don't get distracted by all the numbers. Focus on the question that matters most. Does the interval contain 0? Every interval shown here includes 0. That immediately tells us that none of these contrasts provide evidence of a statistically significant difference. A quick scan of the lower and upper limits is often enough to reach the correct conclusion. Our overall conclusion is straightforward. Since every interval contains 0, we cannot conclude that any of these contrasts differ significantly from 0 at the specified experiment-wise error rate. Notice how multiple comparison procedures tend to be more conservative than individual tests. A difference that might appear interesting in a simple comparison often becomes non-significant after we account for the fact that many comparisons are being performed simultaneously. We now move to Tukey's method. Recall that Scheffe is designed for all possible contrasts. Tukey's method is much more specialized. It focuses specifically on pairwise differences between treatment means. Because it takes advantage of this narrower objective, it often produces shorter confidence intervals than Bonferroni or Scheffe when pairwise comparisons are the primary goal. Whenever every treatment is being compared with every other treatment, Tukey's procedure is often the preferred choice. This slide presents the formula for Tukey's simultaneous confidence intervals. Although the notation may look complicated, the structure should be familiar. We still have an estimate plus or minus a margin of error. The major difference is the critical value. Instead of using a t-distribution or an f-distribution, Tukey's method uses a distribution called the studentized range distribution. That distribution was specifically developed to address pairwise comparisons among means. The studentized range distribution is central to Tukey's method. The statistic is based on the difference between the largest and smallest sample means. Think about why that makes sense. If we can control the most extreme difference among the means, then we've automatically controlled all of the smaller pairwise differences as well. This idea provides a very efficient way to protect against false discoveries while maintaining reasonably short confidence intervals. Let's build some intuition for this distribution. The treatment means are random variables. The numerator of the statistic is the range between the largest and smallest treatment mean. That range is then standardized using an estimate of the standard deviation. The resulting distribution depends on both the number of treatments and the degrees of freedom associated with the error term. Fortunately, software handles all of these calculations for us. What's important is understanding why the range is relevant to pairwise comparisons. Let's see Tukey's procedure in action. In this experiment, researchers compared 4 battery types using mean life per unit cost as the response variable. Each treatment was replicated 4 times. The question is whether any battery types differ from one another. Notice that we're interested in every pairwise comparison. That makes Tukey's procedure a natural choice for this analysis. The first step is determining the Tukey critical value from the studentized range distribution. Once we have that value, we calculate the common margin of error. From there, we construct confidence intervals for each pairwise difference. Although there are multiple intervals, the calculation process is identical for every pair. The only thing that changes is the estimated difference between the treatment means. These are the remaining pairwise confidence intervals. Again, the interpretation is straightforward. Look for intervals that contain 0. If 0 is inside the interval, we cannot conclude that the corresponding treatment means differ. If 0 is excluded, we have evidence of a significant difference. Confidence intervals provide a very convenient way to summarize all pairwise comparisons at once. Based on these intervals, some battery types differ significantly while others do not. Specifically, the intervals comparing battery types 1 and 4 and battery types 3 and 4 contain 0. Therefore, we do not have sufficient evidence to conclude that those pairs differ. The remaining intervals exclude 0, indicating significant differences. This demonstrates how Tukey's method helps us identify exactly which treatment means differ while maintaining control of the overall error rate. This slide compares the widths of intervals produced by different methods. Notice that Tukey's intervals are the shortest in this situation. That result shouldn't be surprising. The procedure was specifically designed for pairwise comparisons. Scheffe provides the greatest flexibility, but that flexibility comes with wider intervals. Bonferroni typically falls somewhere in between. This highlights an important lesson in statistics. There is rarely a universally best method. The best choice depends on the scientific objective. Let's return to the heart-lung pump experiment. This time we're interested in all pairwise comparisons among the RPM levels. Rather than focusing on polynomial trends, we're examining differences between individual treatment means. We'll use several multiple comparison procedures and compare their results. This provides a useful opportunity to see how the different methods behave when applied to the same dataset. This slide shows the SAS code used to perform the multiple comparison analyses. Notice that SAS makes the process very simple. The Tukey option requests Tukey confidence intervals. The Scheffe option requests Scheffe intervals. The Bon option requests Bonferroni intervals. In practice, software handles most of the computational burden. Your responsibility is understanding which method is appropriate and correctly interpreting the results. Today we've learned how to make inferences about treatment means, construct confidence intervals for contrasts, investigate trends using orthogonal polynomials, and control experiment-wise error rates using multiple comparison procedures. These techniques are fundamental tools in experimental design because they allow us to move beyond the overall ANOVA F-test and answer specific scientific questions. Next time, we'll expand our focus beyond single-factor experiments and begin studying multi-factor designs. We'll learn how multiple factors can influence a response simultaneously and, most importantly, how interactions between factors can reveal relationships that cannot be detected in one-factor experiments. Make sure you're comfortable with today's material because many of the concepts we've discussed will carry directly into the multi-factor setting.